In this video, I'm going to show you how to find the area between curves expressed as a function of x. So here's our first question. We want to find the finite area bounded by the curves f of x equals 9 and g of x equals x squared. And the first step to doing this is always to draw a graph of the region that you want to find the area of. So we'll go ahead and set up a set of axes, and we'll graph both of these functions. First of all, f of x equals 9. That's just a horizontal line straight across the y-intercept of 9. And then the function g of x equals x squared, this makes a parabola. And we want to find the finite area bounded by these two curves. In other words, it's like these two curves form walls around some room in the coordinate plane. This is the room here, and that's what we want to find the area of. So how can we do that? Well, the answer is we treat it kind of like a Riemann sum. We break up the region into a bunch of small rectangles, like this one here. And if we enlarge that rectangle, and we think about computing the area of this rectangle, we can do so by figuring out the dimensions of this rectangle and multiplying them together. First of all, what is the height of the rectangle? Well, if you think back to the graph, the height represents the distance, the vertical distance between these two curves. And we can represent that as the top curve minus the bottom curve. In this case, the top curve is f of x, which is 9. So we'll have 9, and then we have to subtract off the bottom curve, which is g of x, which is x squared. So the height is 9 minus x squared. So this height here is really a function of x, and that makes sense because the height is changing. For example, compared to this height here, if we move x over to the right, then we're looking at a rectangle which has a shorter height. Whereas if we move it over to the left, for example at x equals 0, then we have the longest rectangle which has a full height of 9. Okay, and how about the width of the rectangle? Well, the width is just some distance in the x direction. It's a really small distance. In fact, an infinitesimally small distance, just like we use in Riemann sums. And the way we write an infinitesimally small distance along the x-axis is with dx. Now, the area of this rectangle here just comes from multiplying these two dimensions together. So we have 9 minus x squared times dx. And then to get the entire region here, to sum up all these rectangles, what we do is we take the integral. But there's still one thing that we're missing. Do you see what it is? Remember, we want a single concrete number to come out for the area here. But as it stands now, this integral is indefinite, so it's just going to give us an antiderivative function. We want a physical interpretation, an area under this curve. So what we need to do to make this integral come out to a single number is to put bounds on it. And the bounds will just say where the rectangles start on the left side here, and where they end on the right side here. And those x-coordinates are just the x-coordinates where these two curves, g of x and f of x, intersect. Their intersection points are here, and you drop it down to the x-axis, and that's where your bounds are. So we see one of the bounds is at -3 units. That's our lower bound, so we fill that in for our lower bound. And the upper bound, the rightmost bound, comes from this point of intersection, which drops down to +3 units. So upper bound is +3. Now, this was easy because we had a graph, so we could tell from the graph, but if you ever don't have a graph, and you want to find the points of intersection, remember that you can just set the functions equal to each other. So you could have x squared equals 9, the equation to solve for your points of intersection, and you'd solve that, and you get x equals plus or minus square root of 9, which is 3, and that gives you the bounds. Alright, so now we've got our integral that we have to compute, and all that remains is to compute it. So let's focus in on that integral, and let's evaluate that integral. So first we have to take the antiderivative. The antiderivative of 9 is just 9x, and then the antiderivative of x squared can be computed using the power rule, which says for integrals we increase that power by 1, so x cubed, but then we have to multiply by the reciprocal of that power, so 1/3. And now that we found the antiderivative, we just have to evaluate at the bounds and take the difference. Evaluating at the top bound, x equals 3, we have 9 times 3, which is 27, then minus 1/3 of 3 cubed. 3 cubed is 27, and 1/3 of that is 9. Alright, and then we plug in the bottom bound as well. 9 times -3 is -27, then minus a third of negative 3 cubed, and negative 3 cubed is negative 27, and a third of that is negative 9. So we evaluate these two expressions. 27 minus 9 is 18, and then that's minus negative 27 minus negative 9, so negative 27 plus 9, which is negative 18. And we've got 18 minus negative 18, which is 36. And there we go, that's our final result. That is the finite area bounded between the curves f of x equals 9 and g of x equals x squared. And really what that means is 36 square units, but in practice we usually don't bother writing down the square units. Just to leave it as 36 is fine. Now that we've done an example of finding the finite area bounded between two curves, let's do another problem. For our next problem, we want to find the finite area bounded by the curves y equals x squared plus 2x plus 1 and y equals 2x plus 2. But this time we're not given a graph. So how do we approach the problem? Well, one option is to create a graph of our own, but in practice that can take a lot of time. We know that we're just going to be breaking up our region into rectangles. These rectangles will be very, very thin. They will have infinitesimally small width, which we write as dx. And then the vertical height will just be the difference between the functions. Now, of course, at this point, we're not sure yet in which order we should subtract the functions. Should we do x squared plus 2x plus 1 minus 2x plus 2? Or should we do it the other way around, 2x plus 2 minus x squared plus 2x plus 1? Well, remember, we want to do the top function minus the bottom function. So we need to decide between these two functions which one is higher and which one is lower. And whether a function is a top function or a bottom function, that usually depends on the region of integration. In other words, the left and right bounds for x. So that's the first thing that we have to do. We have to find the bounds for x. Now remember, the bounds come from the points of intersection. So we have to find the x-coordinates at which the functions intersect. And we can do that by just setting the two functions equal and solving for x. So we'll have that x squared plus 2x plus 1 is equal to 2x plus 2. That's our equation that we use to solve for the bounds for x. And we can solve that by just subtracting the 2x and the 1 off from the left-hand side. All that will remain on the left-hand side will just be the x squared. And then on the right-hand side, 2x minus 2x is 0, and then 2 minus 1 is 1. So x squared equals 1, and we take the positive or negative square root to get x equals positive or negative 1. So that means our integral will be running from negative 1 to 1. It'll be going between the bounds. And now that we've figured that out, let's go back to thinking about which of these two functions is the top function and which is the bottom function. An easy way to figure that out is just to choose some x value that's inside of our region of integration, in other words, that's between negative 1 and 1, and we'll just plug it into these two functions and see which one is higher. I think the easiest x-coordinate here would just be 0. 0 is between negative 1 and 1, and it's really easy to plug into these two functions. For example, in the first function, if we plug in x equals 0, all the terms are 0 except for the 1. So we get out that y equals 1 when x is 0. And then for the second function, when we plug in x equals 0, all that remains is this 2, the constant. So y equals 2. And since 2 is higher than 1, we see that this function y equals 2x plus 2 is actually the top function here. So that's what goes first in the difference of functions. We have 2x plus 2, and then from that we subtract the other function. So minus x squared plus 2x plus 1. And this is of course an integral with respect to x. So we put a dx at the end. So all that remains is to simplify and compute this integral. First we'll simplify it, so it becomes the integral from negative 1 to 1. Our highest degree term is an x squared, actually a negative x squared. And then 2x minus 2x cancels, and then 2 minus 1 is just 1. So negative x squared plus 1. And that's what we're really integrating here. Now this should be a pretty straightforward integral by now, so I'll just leave it to you to evaluate it and I'll tell you the result. The result is 4/3. That's what you should get when you evaluate the integral. So that 4/3 is our final answer. That is the finite area bounded by the curves y equals x squared plus 2x plus 1 and y equals 2x plus 2.